So problem 2. So problem 2 has a conducting sphere of radius 10 centimeters. So I may as well draw something. So here's my conducting sphere. I'll say the radius is 10 centimeters. And it says that there is a wire that's bringing current in. So I'll say that this is the wire that's bringing inbound current, but there's also a wire that is taking charge away. So there is an I out current as well. And it says another wire, so it actually gives the inbound and the outbound currents. So the inbound current is just a little bit bigger than 1 amp. It puts 3 zeros, that's a dot, not a comma. So 3 zeros, 2 zeros, and a 2, and then another 0, I guess for significant figures. And the units are amps. So then the outbound current, so there's in and out, is actually just all zeros. So it's a 1 dot, 1, 2, 3, 4, 5, 6, 7 amps. So, and it says how long, so what is the amount of time it takes for the potential to increase by 1,000 volts. So presumably, because of the difference in the inbound and outbound current, it looks like the inbound current is a little bit bigger than the outbound current. So I in is bigger than I out. And so what this means is that the charge of the sphere is growing in time. And this charge growing in time must be why we expect the voltage to be increasing. And this charge growing in time, it's actually that we can go ahead and say that the rate of change that the charge is going to grow in time, so it's growing, so it's definitely bigger than 0, but we can say actually more than that. It's actually the difference of the inbound charge and the outbound charge. So this is saying that it's slightly bigger than a coulomb per second showing up at the sphere, and exactly, well, with 7 zeros exactly, but essentially just 1 coulomb per second leaving. And so this thing right here is actually the difference between the inbound and outbound currents. And that difference, so I've got, there's milli, right? If I go 3 zeros over, that's milli. If I go 3 more places over, that's micro. And that'll put the 2 in the microamps place. And so this dq by dt is 2 microamps, but an amp is a coulomb per second. And that's how we're going to figure out time, because of that per second aspect. So this is the rate of growth of the charge. So how does, right? So we've got this 1,000 volts. So the way that so this, remember, it was described as a conductor. And I bet you this 1,000 volts is with respect to infinity. So I'll just put that out there. So hopefully you can recall some things about voltage or potential difference. There was a definition of the potential for a point charge. So a point charge, so for example, a point charge for could be called Q. So the potential is only a function of the distance you are from the charge, and it doesn't matter in which direction you are away from the charge. But this potential is, how does it go? It goes Q over 4 pi epsilon naught times R, but all on the bottom, right? So charge over that. And this is the type of potential that could be, have the value 1,000. But it says it's like increase by 1,000 volts. So this story could be that we start with V equals to 0, and we wait an amount of time, delta t, that we're interested in, and we finish, right, because we're accumulating charge on this conductor, we finish sometime later with the voltage of 1,000 volts. I bet that'll be good enough, right? So, but this is kind of indicating that we could start at, 2,000 volts and wait the same amount of time to get to 3,000 volts. And it turns out that that's actually how the potential works. If we wait for twice as much charge to show up, you will just simply have twice the voltage. There's a linear relationship between voltage growth and charge growth if you have everything else the same. But anyway, so let's go over here. So I have this difference in, so question is what Q for V equals to 1,000 volts, right? So what Q, what value of charge, and then, we've got dQ by dt, so we can say how much time we need to wait before that amount of charge shows up. Okay, so may as well start here. So 1,000 volts, that's the potential. And the question is, well, this is a function of R. So for conductors are actually equipotential volumes because the electric field inside the conductor is 0, so the potential can't change if you wander around within the conductor. So everywhere on the surface of the conductor, as well as internal to the conductor, is going to have the same value of potential. So why don't we just solve for at the surface? So we're going to say that 1,000 volts is the potential at 10 centimeters away. This is kind of a shell theorem argument as well, but it's the potential difference at 10 centimeters away at the surface. Right, so let me put this in here too. We're actually using the shell theorem here, which is about electric fields, but potentials related to electric field. So anyway, so 1,000 volts is the potential at 10 centimeters. That's at the surface of our isolated conductor here, except for charge showing up. So this is 1,000 volts, is our unknown Q, and then our 4 pi epsilon naught 10 centimeters, like this. Okay, so check this out. I can solve for Q. So Q equals, it must be 1,000 volts times, so I just multiply all of this stuff up to the top against the 1,000 volts. So I'll go 4 pi epsilon naught times 10 centimeters, like that. So this is Q, but the question is not about the charge, it's about delta t, right? The time. So this is pretty cool. This says that the time rate of change, right, of the charge is 2 microcoulombs per second. So we're going to get a certain amount of charge that's required in order to have 1,000 volts, right? We're waiting for the time to increase by 1,000 volts, but we're doing it specifically for 0 up to 1,000 volts. So what we need to do is think about how does charge accumulate? So this is what we're going to do. We're going to say that Q, the reason that we can have charge is because a current was flowing for our amount of time, like this. And this current, though, is not either one of these. It's actually the difference between the 2 microcoulombs per second. So we'll put in 2 microcoulomb per second. That's the current. That's the rate at which charge collects here if it comes in at this amount and leaks away at this other amount. So can you see that we have a delta T now? Oops, sorry, it's right here. So I've got Q, all of this stuff, and I've got delta T times I is also equal to Q. So I'm going to set this thing equal to this thing and solve for delta T. So let me do that on the next page. So I've got, I'm going to copy the expression over. So the expression is, 1,000 volts times 4 pi epsilon naught times 10 centimeters, all these things, is equal to 2 microcoulombs per second times our delta T that we're interested in discovering the value of. So of course I can divide both sides by 2 microcoulombs per second, and we can write that delta T is equal to 1,000 volts 4 pi epsilon naught 10 centimeters, and then divide by 2 microcoulombs, and then per second, the second actually, since it's per second, I'm going to put it up on top, right? That's what happens when you divide by a fraction. So the units comprise a fraction, and you just take the numerator, you leave it downstairs, but you take the denominator of the thing that's on the bottom and you put it up top, right? So that's how you divide by a fraction. You just multiply by the inverse. So here's the inverse. It's the second per 2 microcoulomb. Okay, so bunch of stuff that we can put in values for. Let's see, what's a smooth way to do this? I'm not sure that we're going to come up with a very smooth way. But anyways, so here we could do this, like 4 divided by 2 is a 2. And then 1,000 times 10 is 10,000, but 10,000 is 10 not to the third, but the fourth. So 2 times 10 to the fourth. So 4 over 2 is 2. 1,000 times 10 is 10 to the fourth. And then I've got pi epsilon 0, which I'll need to go. I never remember the value of epsilon 0. Some of y'all do. Pi is still around. I've got the volt, the centimeter, so I'll put the volt, the 10 to the minus 2 meters, right? So I'm going to sort of softly also go to SI units. So remember the 10 and the 1,000 got put together for 10 to the 4. So the centimeter is 10 to the minus 2 meters. I've got the seconds, and then I'm dividing by, so is the 2, nope, the 2 is not there because it mingled with the 4 and made that 2. So downstairs I've got the 10 to the minus 6, that's the micro, and then the coulomb. And I think I've done everything right. So what's interesting is this seconds is the only thing that's going to get left over when we go through and we divide and multiply all the things that are involved here. So remember that the volt is, what's the volt? It's a Newton So it's a joule per coulomb, right? And a joule, another way to understand the joule that's going to be nice in this case is the Newton meter. That's the joule. So I still got the coulomb. So the volt is a Newton meter per coulomb. Yeah, that looks like a electric field is newtons per coulomb, and I multiply by a distance to get voltage, or potential difference. Okay, so I'm going to remember that. Epsilon 0 is 8.85 times 10 to the minus 12. And then the units are coulomb squared per Newton meter squared. So coulomb squared per Newton meter squared. So I can put this epsilon naught in there, and pi I know. The volt I just... So let's go ahead and do that. So, yeah, okay. So it's 2 pi 8.85. So 2 pi, there's the 8.85 times 10 to the minus 12. So that's epsilon 0. Okay, and then I've got 10 to the 4th, 10 to the minus 2, over 10 to the minus 6, right? So I've got the 2, the pi, the 8.85, 10 to the 4th I put there, 8.85 times 10 to the minus 12, the volt and the meter and the second. So I'll just do the volt and the meter together and leave the second for later. I'll put so coulombs on the bottom. The volt is a Newton meter per coulomb, right? That's from the volt. I've got another meter from this meter here. I've got the coulombs on the bottom, but the thing that I didn't bring along quite yet was epsilon 0. I mean the units of epsilon 0. So the units of epsilon 0 are coulombs squared. I'll just extend it. So newtons meters squared. So that's the units on epsilon naught. The other units actually came from elsewhere. The volt and the meter and the coulomb. Okay, so this coulomb on the bottom is in the denominator, so it can tack on to be with this coulomb in that denominator, and then all of a sudden you see why keeping the units is so nice. Ooh, speaking of keeping the units, I've got this second left over. So seconds on the outside, and so we get to swipe away a whole bunch of stuff. So actually I built up this coulomb to be coulomb squared because it took it from there, and then all of this is the inverse of all of that, so they multiply to be 1, and everything inside the square bracket, as promised, is unitless. It's dimensionless, and the only dimension is the dimension I kept on the outside, which is time. And that's what we're calculating. We're calculating a time. So it's very nice to see all that happen. Let's work on the factors of 10 for a second. So 10 to the minus 6 on the bottom is 10 to the plus 6 on top. And 10 to the plus 6 and 10 to the plus 4 combine to be 10 to the 10th. So I've got 10 to the positive 10. So when I multiply by 10 to the minus 2, that'll be 10 to the positive 8. And then 10 to the positive 8 times 10 to the minus 12 is 10 to the negative 4th. So let me clean this up for a second. So I've got 2 pi times 8.85, right? And then I have, it turns out that this is 10 to the minus 4. And then the units that are left over are seconds. So after tons of me talking, I get 2 times 3.14159 times 8.85 equals 55.606. So I'm going to keep, I've got 3 sig figs here. I really had 2 sig figs here because they carefully gave us an extra significant figure here and here. So really the difference in current was 2.0 microcoulombs per second. The 1,000 volts, they specified 1,000, so they must have specified exactly 1,000. That's exactly 4. This is 10 centimeters. I'm going to assume that they meant this as 2 sig figs too. So I'm going to keep 2 significant figures, which means that this is about 56, right? Rounding, so it's about 56 times 10 to the minus 4 seconds, and that's my answer. I wonder if it's correct. I don't really have a good fast way to say why it seems correct, honestly. So if I look at this time, it's a small amount of time, which seems kind of crazy because we are looking at a really small difference in currents. So it looks like it's taking just a small amount of time at 2 microcoulombs per second to build up an extra voltage of 1,000 volts. But maybe this is, I don't know, like honestly it's hard to say if I have a number that makes sense in terms of its size. But I do have the right units. That's good. What can I learn from this problem? This is kind of a neat thing right here, that the charge was collecting because the current going in to the object was bigger than the current leaving the object. If the tables returned, then we would watch the charge on this thing decrease, and the voltage would decrease instead, not grow up to 1,000 from 0, but maybe decrease down to negative 1,000 volts from 0. Yeah, I got to use this little formula where the charge sort of accumulated, or the charge that passed along as the current, is just the current times the time you wait. Okay. Yeah, so a couple things, but that's problem number 2. Sort of took a long time, I think, mostly because it'd probably take you less time if you do it yourself, because you don't have to talk while you write. Okay, so problem number 10 says we have a current density in a certain laboratory wire that has a circular cross-section of radius 2.00 millimeters. So 2.00 millimeters. I have a circular cross-section, so this is the cross-section of a wire, and this is the radius of it. And it says that the current density has an interesting profile. It's equal to 3 times 10 to the 8th times r squared. So 3.00 times 10 to the 8th times r squared. So this, when I write it down, it's a coefficient times a variable squared. This looks like a parabola. This probably doesn't matter to say this, but that's what it appears. And the distance r is read from the center, so we're treating r as the radial distance from the center of this wire. Yeah, so interesting. It's got this. There's some interesting instructions on how to use this, and so I'm going to think about that for a second. It says J in amperes per meter squared. That's what you're going to get as the units on J if you put in, if meters if you put in R in meters, right? So if I put, so this is in millimeters, so we're gonna put in values that are like 10 to the 10 to the third and stuff. No, 10, excuse me, 10 to the minus 3 in meters. So 10 to the minus 3 squared is kind of the stuff we're going to see. So there's J. So what I like to do, actually, I wish the book did this, but of course it doesn't do that because, it puts too much writing in their problems. But I'm going to put these units in here. So I know that this is going to be amps per meter squared if I put meters in as the unit for R. So that means that what this needs to do, so check this out, it's 3.00 times 10 to the 8th. It's going to return amps per meter squared, but I've got this R squared, and if I put R in meters here, what I need is an extra 1 over meters squared, because this right here will, when I put in R in meters, I'll lose all the units. So that means the thing inside the brackets will have no units left, but it will be a number. It's a number with no units. And then here's another number with no units, and then here's the units, amps per meter squared. That's what J needs to be. So that means that this thing right here, the way I have to understand it, is 3.00 times 10 to the 8th amps per meter to the 4th times R squared. And so you can see that this is how this will work. If I put in R in meters right here, it's the meters will get squared, and then meters squared over meters to the 4th is per meter squared. So the units are going to work out. The amps have nothing to cancel against or anything like that. So, but anyways, question is the current which flows between 9/10 of R and all of R. So it's actually, they give us a few significant figures. So it's 900 R and R. So R is the outer edge, and 9/10 of R is a little bit in. So we actually want only the current that flows down this wire in this part, just that part. Okay, so when J, the current density, depends on position, the way you get the current is you have to do an integral. Like, there's no shortcut. You actually have to perform the integral. And the integral is J times a area element, right? dA. So this A is not amps. That's amps. That's the unit of the amp. This is a small element of area. So because J is so-called cylindrically symmetric, so J has cylinder symmetry, that is, J is only a function of R. It's not a function of any other spatial variable. So when you have a function that's only a function of R, it's got this cylinder symmetry. In the case of cylinder symmetry, the type of area element that's really useful is to take a very thin ribbon or strip. So the length of this thing is the circumference. It's 2 pi r, and the width of the thing is dr. So dr is a small radial difference or a small distance. And the length is simply at r, it's the circumference. So if I take this length and I multiply by this width, I get the small area. So the small area is 2 pi r dr. And that's what I'm going to put right here. And so now you can see that the integral has a parameter, this radial distance parameter, and here are the bounds on that dummy variable or that parameter. So the current is just the integral from 0.9 r up to all of r of j of r, so j of r dA. So integral from 0.9 r up to r. So j of r has this business here. This is the 3 times 10 to the 8th amps per meter to the 4th, r squared. So 3 times 10 to the 8th amps per meter squared. Meter to the 4th, excuse me, amps per meter to the 4th, r squared. So this is j of r. So that's j of r. But we're not finished because we need to tack on the dA. And the dA is another couple of things, including the r and the dr. So this is dA. And so the integral, so I've got the 2 and the pi and the 3 times 10 to the 8th amps per meter to the 4th. They can come out because they are constants. So 3.00 times 10 to the 8th amps per meter to the 4th times 2 pi. And then I get r times r squared is r cubed, but that has to stay inside the integral. So there's the r cubed dr. I can go from 0.9r up to all of r. And so you can see what's about to happen. So the integral goes r fourth over 4. So you get 3.00 times 10 to the 8th amps per meter to the 4th, 2 pi over 4. And then it's r to the 4th evaluated at capital R and 0.9 r. And this is going to give you some answer, but check it out. So r is a distance, right? So r is a distance. So when I put that in to r to the 4th, you're going to have a distance raised to the 4th power. So I'm going to put this in as, maybe I could convert this to meters. Go ahead and do it now. I could do it later, but anyways, that distance to the 4th is going to cancel with this unit meter to the 4th. And you might have a conversion factor as well, like some factors of 10 around. But anyways, you can see that the only unit left is going to be the amp. And we are calculating a current. And that's what has to happen. So you still need to do some work. Still work to do. But this is the right path. So just because I calculated something for you with a lot of care in problem number 2, I'm going to let you finish this. But all you got to do is evaluate capital R to the 4th, where capital R is 2 millimeters. Subtract 9/10 of 2 millimeters raised to the 4th power, right? Don't forget you have to raise this to the 4th and that to the 4th. Take their difference and then multiply the difference times this number over here. So you still got some work to do, but you can see that the units are going to work out. An important thing that I showed you, I think, is the judgment call that because you have this cylinder symmetry and because J is actually a function of the radial distance out, you have to do an integral, and the area element, it's always, this is current per area, so I need to multiply by an area to get a current. So here's the area element, is this really narrow, like this is how narrow it is. This is the width of a little ribbon of area, and this is the length of it. It's just the circumference around the circle. I think that some of those things are kind of crux moves. Another crux for me is to make sure I've got the right units on things that look like constants, because then when you work stuff out, you can see that, yeah, I'm about to calculate some amps, and that's what a current is. It's not amps times meters, it's not amps per meter, there's no other meters in it, it's just purely charge per time, right? So coulombs per second is what you should get as an answer. If you don't get current as the answer to calculating a current, if you get current per meter or something else weird, you're guaranteed that you made a mistake, is the idea. So let's do problem number 20 next. So here's an interesting problem. So problem 20, problem 20 says a certain wire has resistance R. So there is a wire with resistance R. And the question is, what is the resistance of another wire, a second wire, which is same material, but let's see, it says half as long, so it's shorter, right? Half as long, and half the diameter. Right? And we want to know what is the resistance of this new resistor. So I've got, say, an old resistor, right? And so I could say that's the old one, or the one that we start with. And now we're going to make a new resistor that is not as long, it's only half as long, and its diameter, so we're assuming, I guess it's a cylinder, its diameter is half as much. So let's think about that. So the old resistor, it's made to have a certain length. It's made out of a certain material with resistivity rho. And it's described that the new resistor is going to be made out of the same material. And the resistance it's directly proportional to the length, so the longer of a resistive material that you have, the more resistance you have, but it's divided by the area A, so that's not the amp, that's the area A. And so this right here, let's say that I've got my wire, and it's got cross-section area A, length L, and is made of resistive material rho. And then over here, I've got half the length, same material, but this area is got half the diameter. So let me say, for lack of a better symbol, I'm going to put A star, where A star is the half diameter area. So we want to compare, right? That is, in terms of R old, what resistance is R new? Well, if you have less length, it's pretty easy. Well, L is going to be smaller, so R old, or R new with the smaller length is going to be smaller because of the length. The resistivities are the same, so that's a non-issue. But the area is kind of strange. It's like it's not clear how the area is going to play into this. So what we need to do is we need to figure out what happens if you take half the diameter. That is, let's compare A star and A right now, because that needs to be our next step. So for comparison, let's say that this is A, and A star is half the diameter, so here is A star, because it's half this diameter. So you can see actually A star is actually quite small compared to A. But let's do a little better than that. So you know that the area is pi times the radius squared. Another way to say this is it's pi times the diameter divided by 2, all squared. So you have to square even the 2 on the bottom, right? Because it's r squared. So you get pi d squared over 4. Okay, so let's look at A star. So A star, the smaller area, is equal to pi, but it's not all of d, it's half of d, right? D over 2. So I'll put in d over 2, but d over 2 needs to get squared, and we still are dividing by 4. So what this looks like is, so d squared over 2 squared is divided by 4. So I'll let you figure this out, but what it looks like is this, right? I get 2 factors of 4, and what this looks like is 1/4 of the area A. And this is how we can compare the areas. And if we can compare the areas, right, A star is 1/4 of A, right? This is 1/4 of all of this. And so let's go up and build R new. So R new is L over 2 times the resistivity divided by the new area. The new area is 1/4A. And so when you divide by a fraction, you multiply by the inverse. So it puts the 4 at the top, and you get 4/2 L rho over A, which is twice R old. So R new is twice R old. And that's the relationship right there. So some crux moves, right? Some stuff that was difficult was the problem set us up with a piece of information that wasn't easily, like for some people it's easy, and the more practice you would have at doing this kind of thing, you would see through it quicker. But we need to be careful and not make mistakes. So we need to be kind of formal, right? So we need to figure out if I got half the diameter, what does that mean about the area? So we did that kind of analysis, and it turns out that at half the diameter, I end up with 1/4 of the area, because the area is dependent on the diameter squared. So if you half the diameter, that ends up as diameter squared over 4, and so that's the 1/4. But what's really nice though is R old, we actually used some symbols where we could figure out when we calculated R new, we could use the same symbols but with fractions in different places. And the fractions mix up. In this case, it gives us a factor of 2, and that relates for us in a formal way R old and R new. So we didn't hand wave at all, right? Didn't guess. We followed our nose and didn't make any approximations or guesses, and yeah, and out pops the answer. So that's number 20. So let's do number 24 next. And 24, it gives us some information inside of a graph. So I'm going to try to reproduce this graph right now. On the vertical axis is electric field, and it's given in magnitude, so I'm going to not put a symbol. And it's the electric field as a function of position along an x direction. And the graph is kind of strange. It says that between x equals to 0 and x equals to 3 millimeters, the value of the electric field is constant until the 3 millimeter mark. But between 3 millimeters and 6 millimeters, the electric field is bigger. So I'll draw it up here. And then from 6 millimeters to 9 millimeters, the electric field actually has the smallest value. I'll draw it here. So this is the graph picture, and it's split up into regions. So this is considered region number 1, and this is region number 2, and this is region number 3. So I'll just do little dotted lines to separate the regions. And yeah, it actually doesn't describe the electric field on the outside of 9 millimeters, but I'm just going to drop the line to 0. So the electric field is given in this graph in terms of a strength or a scale called E sub s, where E sub s is, let's see, it's 4 times 10 to the third. And it's given in terms of units of volts per meter. Yeah, so I'll just leave that like that for now. And then if you look in the scale, the graph is really careful. It's split up into, so they take E sub s and they split it up into 8 parts. And I wasn't too careful about the heights, but if you count up the parts, this electric field is 5/8 of E sub s, and this electric field here is 3/8 of E sub s. So the electric field inside of region 1 between 0 and 3 millimeters is 5/8 of 4 times 10 to the third volts per meter. And then in region 3, it's 3/8 of 4 times 10 to the third volts per meter. And then in this section right here, it's all of E sub s. So in region number 2, region number 2's got the full strength of the electric field. And this electric field goes with a particular problem setup. So there is a voltage source here. So for lack of a better letter, I'll just say that the battery's got voltage V, or actually that's the letter used in the diagram. So, and then over here is some strip of resistive material, and that's the only thing in the circuit. So I've got a wire from the top positive piece of the battery that goes to the top of this resistive strip, and then a wire that completes the cycle or circuit down to the negative part of the battery there. And the idea is this electric field graph is a picture of the electric field in the 3 regions, 1, 2, and 3, of this resistor. So in the diagram in the book, it says that this is the x equals to 0 end, and this is the x equals to 9 millimeter end. And so this is my resistive device. And yeah, so the question is if, oh, actually, so let me continue. So it describes this resistor as having 3 different radiuses. There's a radius R1 for the first portion of the resistive strip. There's a radius R2 for the second portion, and there's a radius R3, which is actually given. So the radius of section 3 is 2 millimeters, right? And the question is what are these, not resistances, what are the radii of the other 2 parts of the resistive strip if the radius of the third part is 2 millimeters? So they're suggesting that this resistive strip is actually something that might look like the following. So I'm about to guess the relative radii of the strip, right? Just for the sake of having a picture. So these electric fields with the regions 1, 2, and 3, I'm going to guess that in region 1, I have some medium value of radius. In region 2, I'm going to guess that I have a really large radius. And then in region number 3, I'm going to guess that I have the smallest radius. It's just a guess, and I'm likely going to have guessed wrong. But the idea is this is the resistive strip. Here is the battery. And you could imagine that this is a little bit more of a cartoon drawing of this more schematic picture here. So this is region number 1, this is region number 2, and this is region number 3, and the radius of region number 3 is 2 millimeters. The book, or the problem, also is careful to state that each of these regions has the same resistivity. That is, they're all made out of the same material, so they each share the same resistivity. Okay, so I've got lengths, right, in this problem. Radii are asked for, right? They're the subject of the problem. So lengths and radii. Resistivity is common, but the point is it's also mentioned, right? And I have electric field up here. E field is given, right? And so this problem is asking for radii. It's mentioned resistivity is common to all 3 regions. I have the electric field. I have some lengths, right? They're all 3 millimeters long, the 3 sections. And the radii are asked for. Radii are associated with areas. And so this is sort of beginning to look like a couple things. I know that there is a basic sort of Ohm's law relationship. The basic relationship is if you have an electric field inside of a resistive material, there's going to be a current density J associated with the electric field and the resistivity rho. So in these 3 regions, I have that E1 equals, remember rho is common, times J1, so that's the current density in the region 1, the current density in region 1. I also have, so I have a different electric field in region 2, but the same resistivity, so I'm going to have, in general, a different value of the current density in region 2, and E3 is the same way. So an interesting thing to do is I really want the radii to be incorporated, and I have these lengths. So radii and lengths and resistivity, so radii are areas. So another thing I can write is, for example, the current through region 1 is the resistivity, no, excuse me, it's not that, it's the current density in region 1 times the area, cross-sectional area of region 1, for example. Right, so so this is the relationship between the current and the current density in the area. There's a relationship like that for the current in region number 2. So this is the overall current that flows through region 2, right, where, yep, so it's equal to current density times area of region 2, and there's likewise a relationship in region 3 that looks the same. So the areas are all different because the radii I expect to be all different. I remember that the radius of region 3, I'm given it, but I don't know what J3 is. Okay, so now here is the crux of the problem. It's another realization, so a crux realization. the crux realization is the currents in the three regions, they need to be the same. So the currents in region 1, 2, and 3 need to be the same, and it's because, right? So I'll put BC for because. If I1 is not equal to I2, for example, then charge collects up, right? And in circuits like this, we don't allow charge to collect up. If the current going into region 1 was, say, bigger than the current leaving region 1 and going through region 2, then that means that in between regions 1 and 2, I am building up electric charge. That is, this thing is acting more like a capacitor, or it has a capacitance component. But we're not going to let that happen. This is, right, circuits don't, or like conductive circuits, which is what this is, the idea is we're going to allow the current to be the same through each of the regions. Or not allow it, but we're going to impose it and use it as a crux realization. So if the currents are all the same, then you can see what we can do. So let me move on to another page. So if the currents are all the same, that means, for example, right, let me use something a little bit that we have knowledge of. We have knowledge of the area A3. So I'm going to spend some time and look at the relationship between I2 and I3. I2 is equal to I3. So let me put these two things equal to each other. So since I2 is equal to I3, then we can say that J2A2 is equal to J3A3. And so, but another thing we can say that incorporates the fact that we also know that the resistivities are common, can you see that J2, for example, is E2 divided by the common resistivity rho. So let me go and put that. So this is E2 divided by the common resistivity rho times A2 is equal to E3 divided by the common resistivity rho times A3. And this is big because we can take this and say E2, which we actually know the value of. E2 is the electric field in region 2. It's all of this ES value, so it's got a value. So E2 I know. I don't know rho, but I do know it's common in all of the regions. And then I have pi times the radius of region 2 squared, right? That's the area of region 2. And it's equal to the electric field in region 3, which I know, it's 3/8 of E sub s. I also know the radius of region 3, so I can square it, multiply by pi to get the area of region 3. And then I have to divide by this unknown but common resistivity rho. And now you can see how the problem plays out. We don't know the resistivity rho, but it turns out it doesn't matter what it is. It only matters that it's the same on both sides. Pi is the same on both sides. And so I can fill in. So E2 is all of ES. So it's 4 times 10 to the third volts per meter. That's what E2 is. And then R2 is the unknown, and it's squared here, equals to, so E3 is 3/8 of that number, so that's 12/8. What's a good way? Oh, 3/2, right? So 3/2 times 10 to the third volts per meter. That's E sub 3. And then R sub 3, I actually know the value. It's 2 millimeters. So it goes 2 millimeters all squared. So you're going to have to square the milli, right? So that 10 to the minus 3 is actually a 10 to the minus 6 after squaring. So you'll have to remember that. And the 2 gets squared as well. So this is going to give rise to an R2 value that you can answer, right? And it's the same game to figuring out R sub 1. So I'm going to leave this for you, so you can go finish it. And you might compare your answers to my drawing here. I wonder if I was correct. So in region 3, I imagined having this 2 millimeter radius, and I thought, oh, that seems small. And then I was like, well, maybe the radius and the electric field strength in that area are going to sort of go with each other, so that the smallest electric field is going to have the smallest radius. But I imagine that what you're going to find is something different from this. I wonder if actually region 3 should be the biggest radius. Region 2 should be the smallest radius, and region 1 is still the middle radius. So I think this picture, actually region 2 should be the skinniest part of this resistor. But I'll let you, you're about to find it right here. Yeah, okay, so in fact you can kind of see that that's what's going to happen if you look at these numbers. I've got a 3/2 on one side and a 4, and that 4 is about to go to the downstairs, and R2 is this less than 1 value, right? Times the R3 squared. So yeah, that's what you're going to find. Okay. So let's do another problem. Here's a problem that involves a graph as well. This is problem number 28 in the book. Let me open up the book again in my computer. 28. So 28 says, so this is another graph problem. It gives a graph of information. And graphs are really nice ways to sort of summarize information. So the information given in the problem is there is a voltage versus position again. Actually, this is voltage versus position, which is different from the previous problem in 24, which was electric field versus position. So this is pretty nice. We can see 2 different uses of a graph. And this graph says that the voltage decreases as a straight line from 12 microvolts, right? So that's a really small voltage, over the distance of 3 meters. 3 meters is really far, right? It's about 3 feet per meter, so that's about almost 10 feet. So over a distance of 10 feet, I get to lose this really tiny voltage, right? Microvolts. So that's like 10 to the minus 6 volts, or 10 times 10 to the minus 6 volts. So just based on the data alone, small voltage drop, right? This is a drop. It's dropping from 12 to 0 microvolts over a large distance. So this is something that's kind of remarkable. So I may as well remark on it and think about it. Okay, so then the problem goes on to say, this is the case, right? This small voltage drop over this really, really long length. This is the case for a copper wire. And copper wires, something that's remarkable about copper wires is very low resistivity. So I wonder if low resistivity and small voltage change or voltage drop over really long length, they must all be sort of related issues, right? So, and yeah, and it turns out that that is the case. So the resistivity of copper, just because I'm like, yeah, copper is supposed to be this really good conductor, so its resistivity is really small, I'm just going to, even before I finish reading the problem, or maybe I would scan the problem real quick and make sure that this maybe wasn't an empty sort of direction to go in. It turns out that the resistivity of copper is really small. I go and look in the book. It's in the book. It's actually in two different places in the book. 1.69 times 10 raised to the minus 8. And the resistivity is mentioned with units of ohms times meters. Ohms times meters. So that's just from the book. So I went and looked in a table in the book. So the book gave us this. All right, so let's read the problem a little more. It says that the wire, so this copper wire, with this small voltage drop over the long distance, so 12 microvolts over the distance of 3 meters. So this copper wire is actually a long cylinder, right? It's a long cylinder. It's 3 meters long, and it has a really small radius described as 2 millimeters. And it says, so the book says, what is the current in the wire? So what is the current in this wire? So it's like, I wonder how I'm going to figure this out. Like when I think of current, I think of a current being driven through a resistor because it's connected to a battery, right? And so normally in order to figure out the current, I need to, right, I want to do something like this. I times R, so this is my current, is equal to the voltage. So I want to do something like this. But I don't know, it doesn't seem like I have a voltage or anything like that, although I am given it's 12 microvolts of a voltage drop over this crazy distance of 3 meters. So maybe this 12 microvolts is my voltage. And then in fact, if you think about it, actually, this right here could be this device, this resistive device. And actually, that's the way we're going to think about this. This is how to think about this problem. So the only way to give myself 12 microvolts over this section of wire is to imagine that I do actually have that particular situation. So I've got infinite conductivity, let's say. It's kind of fake to say it that way, but here's how we might be able to model what's going on. Here is the 3 meter long strip of copper of really small radius. And then I'm going to connect another infinitely conductive piece of thin wire. And I'm going to say that I'm going to apply 12 microvolts across all 3 meters of that copper. And I'm going to check what is the current, right? The goal is the current. What is the current in this wire? Right, that's the question. So what can I do? I've got resistivity, I've got length, I've got the ingredients for an area, and I know that the macroscopic resistance, if I know details like the length and the area, it's rho times the length divided by the area, like this. So I'm talking about copper. So the resistivity that I need to put there is this resistivity here. So I can actually describe the resistance of this. It's essentially of a very highly conductive wire. So it's 1.69 times 10 to the 8th ohms meters. That's the resistivity. Sits right there. The length is 3 meters. So this meters and this meters is going to combine and make a meter squared. and then I divide by an area built out of the radius right there. So it's pi times 2 millimeters squared. Okay, so this resistance, oops, not 10 to the positive 8, 10 to the minus 8. I got scared. I was about to build up this large number for capital R, but really I need to expect that capital R for a copper wire is going to have very low resistance. So I got to make sure I got the minus 8 there. So you can see that the meters here, meters squared, are going to cancel with a meter squared on the bottom, but I have this milli, and milli squared is, it's going to be like a millionth after you square it. So I've got 1.69 divided by pi, which is 3.14, you know, however many significant figures you want to keep around. On the bottom is a 2 squared, so that'll be a 4, right? And then I got milli, so milli squared is actually 10 to the minus 6 on the bottom. The meters squared comes from, you know, the millimeter squared. And then up top is a factor of 3 that's extra. So it looks like this, and then I've got the 10 to the minus 8. Like this. And then I've got ohms meters squared on top. Like that. And so you can see that the meters squared are going to cancel. The 10 to the minus 6, I can put it upstairs with the 10 to the minus 8, but when I put 10 to the minus 6 up top, it becomes 10 to the plus 6. So 10 to the plus 6 times 10 to the minus 8 is 10 to the minus 2. So it goes 3 times 1.69 times 10 to the minus 2 over 4 pi, just numbers, and then I've got ohms left over. So I've got the resistance is this thing right here, so I can put in the resistance there, and if my model assertion is correct about the 12 microvolts as being a battery that's pushing the current through my resistor here, then I can just solve everything. I got 12 microvolts. I have this particular resistance that I still need to calculate, right? And I can solve for the current. But what I want to show you, so I want to show you a different way to do this, which honestly is a cooler way. So in this way of doing stuff, right, this will get you the answer. I had to assert a model for how I was using this thing. I was like, maybe it kind of looks like this, and actually that's a reasonable assumption. It's a good modeling. But what if I wasn't inspired like this, right? Let me show you another way to think about this that's actually pretty cool. All right. So another way to think about number 28. Another way to think about 28 is to look at this function. It says that v of x is equal to, so you get 12 microvolts of a drop. So watch this. I'm going to make a function. It's 12 microvolts minus 12 microvolts over 3 meters, right? That's a slope. So I drop 12 over running 3 meters, right? That's a slope. And then I'm going to multiply by x, where x is a number between 0 meters and 3 meters, or it's actually a position. So x is the position, right? And that's the potential function that describes this curve here. And here is something really cool we could do. Remember that the electric field in any direction, including, or in, you know, for us, we're interested in the x direction, or the direction along the conducting piece of material. It's equal to the negative of the derivative of the potential with respect to only moving in the x direction, or thinking about changes in the x position. And so if I do this, I can get the electric field just by taking the derivative of this voltage function. So the derivative, right, is going to pick out the slope. It's going to ignore the constant and pick out the slope acting on the x here. And there is no x squareds or any other x dependence. So it just picks out that slope with this minus sign and that minus sign. You're just going to get 12 over 3, which is 4. And it's microvolts per meter, right? So volts per meter is like electric field units. So I've got microvolts per meter. This would be, yeah, so I'll just leave it like that. So I've got this electric field from this really cool piece of technology that you learned earlier in your book about the relationship between electric field and the derivative of the voltage, right? Yeah. So this is a story from earlier in your work, and I have a value for it, which means that inside of this long copper wire that has a potential difference from end to end, there is this electric field inside of there. So inside, all the way from here all the way to there, because the derivative is constant, right? It's got this constant slope everywhere. So for every x position, or every position along the wire, I've got the same value of electric field. I have the same slope. So this electric field is constant inside of the wire, right? So it's got the same strength everywhere along the wire. So the reason why it's nice to know about electric field is because there is a different Ohm's law than this macroscopic Ohm's law. It's considered like a microscopic Ohm's law that, keep bumping the thing, that the electric field is related to the current density by the resistivity. So I've got the resistivity of copper. That's a piece of information. I've got J, and now I've got E as well. So I can get J. So J is equal to the electric field divided by the resistivity. And the current is, because the electric field is uniform in this material, the voltage only depends on the x direction and not the y or the z. The current is, so the current density will be uniform because the electric field is uniform and the resistivity is uniform. So the current density is uniform. So that means that the current, which is normally this kind of integration, it just breaks down and becomes J times the cross-section area A. So this is J times pi times the radius of my wire squared. And that's what the current is going to be. And this is the goal of the problem right here, is to get the current. And now you can see that I can get the current. The current is, so J is E over rho, and here is E. It's 4 microvolts per meter. That's E. I need to divide by the resistivity, 1.69 times 10 to the minus 8 ohms meters, right? So that's what J is. And then I multiply by pi times, so the wire was a 2 millimeter radius wire. So I can do 2 millimeters squared. And I've got numbers and units for all of this stuff, and you're going to be able to get a current. So this was a different way to do this problem. And in a sense, this is more fundamental because we were thinking in a microscopic way. Over here, this inspired kind of modeling of how to use this wire or how to give the wire the 12 microvolts. This is also correct, but it was a little bit of a leap of faith, honestly, for at least for where you're at in your chapter. But this right here, I didn't take any leap of faith. I looked at the graph. The graph's a straight line with a downward slope. So I made a straight line with a downward slope with y equals to mx plus b. I can get the electric field. The electric field is related to the current density. right? And the rest of it falls out.